Morning, everyone. So welcome to the seminar series again. Today we have a guest, Javier Alcolea. Is that the correct pronunciation of your name, I hope? He is a guest of Hans for the whole week, and I will give a word to Hans to introduce the speaker.
Okay, thank you, Andrew. So it's a pleasure and an honor to welcome Javier, of course. We foresaw a binary talk, but Ivan had to leave, so Iván Gallardo-Cava is a collaborator of Javier in Madrid, but he had to leave early because of family reasons this morning, so it's a pity for him, of course, for us as well, but mainly for him. But we are happy still that Javier is taking up a double role. So
or not.
Yeah,
so we'll see.
Yeah, Javier has been in astronomy for a long time. He is one of the examples of, in Spain, there is a big community of radio astronomers, and I think Javier is one of those examples in which the radio astronomy in Spain is very strong and is very well recognized. So he is coming from the National Observatory of Spain in Madrid. Mm-hmm. I think there are several regions, no?
We have buildings in Madrid, and there is somewhere else, and the telescope is nearby in IvS, okay, where the telescopes are.
Yeah, and so Spain, of course, you have Iram, but also ALMA. They are very well equipped with ALMA, Plateau de Bure, and so on. And so it's a pleasure to welcome him, and he will talk about Post-AGB Tales from the Dark Side. Please.
Thank you, Hans, and it's also a pleasure for me to be here and tell you what we are doing in our group in Spain, although I will focus on what we have been doing in collaboration with Hans in the field of post-AGBs with binaries, but I will do a little bit of propaganda for all the stuff we are doing. Just the dark side, because as Hans said, we mostly do centimeter, millimeter, submillimeter radio waves, which from many point of view, they're pretty dark, but apart from that, there is no other reason for that. And my apologies on behalf of Ivan. He has a serious problems at home. I mean, a health problem with his family. And he couldn't escape. Okay, the talk is about if we do understand how the circumstellar envelopes of evolved stars, whether they are AGB or RGB, I don't care at this point, but these are all AGB stars, can evolve into planetary nebulae. Of course, in the old days, people will say that the circumstellar envelopes around AGB stars are round. They are not round anymore. They present a lot of morphologies. I will show some other later. But from a distance, they still pretty much look spherically symmetric if you don't have a look in detail. If you do the same with planetary nebulae, they are totally different. In the old days, before the HST, people will say that those that were not elliptical or spherically symmetric, I mean the PNs, were the minority, but in fact, is more than 80% of protoplanetaries or planetary nebulae are totally different from spherically symmetric or a small deviation for spherical symmetry. So these are the prototypical shapes and not these ones. Okay. Even this that looks elliptical is not an ellipse, it's just a ring, a thick waist seen with some projection. So it's not an ellipse, it's just ring, what we are seeing from a certain point of view. And after more than 30 years of struggling with this problem, we came with the idea that the only solution for that is that all these guys cannot be single stars. They had to be binaries or multiple system. Otherwise, there is no way to explain the existence of axial symmetry, the emission of high velocity jets, the formation of bipolar lobes, etc., etc. We don't have angular momentum in a single evolved star to justify any preferential access if we don't have a companion. This is not a crazy idea. In fact, about half of the stars of solar type are not singles. It is true that the direct detection of a binary as a companion around an AGB star has some problems. The AGB star is very bright, and the companions are usually very faint because they are or main sequence or white dwarfs, so much weaker. And also, typically, many AGB stars show a strong pulsation activity, and then trying to derive a radial velocity curve is also tricky because normally the amplitude of the pulsation is even larger than the radial velocity shift you expect from the typical companion. It can be done. Huh? As I said, planetary nebulae are not spherical. We already know that more than 50% of central stars for planetary nebulae are not single. And of course, when you know that there are binaries at the center, you know that there is a binary. If you only see one star, you still don't know whether it's a binary that you haven't detected. So that's why I put more than 50%. And in fact, at least 20% of the central star of planetary nebulae are what we call post-common envelopes. They are so close that at some moment the two stars were in the same stellar envelope of the AGB star. So that the AGB star engulfs the companion spirals in, this gravitational energy expels the envelope, and then you are left with two tiny stars orbiting each other at a distance that is smaller than the size of an AGB star. But the star is post-AGB, so there's no way out. And thanks to the work of Lin in the room and his team, in a large program with Alman, we know that these spiral patterns that I showed before in a few cases is in fact the general trend. We also have more interesting cases with funny shapes, but at least this spiraling structure is being the most common. So, and again, the only way of explaining this kind of a spiral structure, R-like structure, is by having a companion. In the case of this spiraling structure, probably companions of around 100 years period or so. What else? Well, in case you doubt these guys are related with planetary nebulas, there are a few examples of planetary nebulas or protoplanetary nebulas where we see the axial asymmetry. In this case, we have multipolar asymmetry. This is bipolar too, and we also see the remains of the AGB envelope reshaped with this cohort of arcs in all cases. These are just 4 examples, but there are many more. So, in fact, these guys are the descendant of these guys after something went bipolar at some point. In terms of evolution, you become a post-AGB star when, because of the mass loss you suffer during the AGB, or maybe some chaotic or catastrophic event, you get rid of all the mantle and you leave the core exposed. Of course, that takes time, and the time you travel from the red part of the spectrum to the blue part of the spectrum depends on how big is your mass loss during this transition phase, and that's something that we really don't know. Post-AGBs are typically stars that are in the making this way before becoming central stars of planetary nebulae that by definition must have at least 3000 Kelvin. So they are blue enough to emit UV photons and photodestroy first the molecules that are present in the former AGB envelope and then ionize the gas. The objects in between, the pre-planetary nebulae, or which are surrounding a post-AGB star, are objects in between that show still molecular rich content, but they also show all these kind of things of asymmetry, etc. This is the group, just a little bit of propaganda. It's not only the OIN, that we have members in the group in other institutions. We have a coordinated project financed by the Spanish Ministry of Science, and this is the typical work we do. We mostly do radio astronomy, but we also have experts in binary orbit calculations. We have experts on post-common envelopes, and we do modeling of the dust emission and of the molecular lines. And this particular research program is focused on understanding the role of the binaries in the shaping of planetary nebulae and protoplanetary nebulae. This is the main goal. Few examples of what happens with AGBs, still AGBs, not in the pre-planetary or planetary nebula phase. The archetype of all long period variables, Myra, is a regular variable that is well known since many years, that has a companion with a period of about 500 years. We have been observing this source with ALMA for several epochs. It's difficult to fit a 500-year period with only ALMA data, but the data is still compatible at least with something which is several hundred years period. There are claims of evidence for residuals in the optical observations, but also, for example, if you have a look at the variation of the SIO masers, which happen to occur very close to the primary, so this is sort of the proxy of the velocity of the primary. There are some evidence of maybe 30-year period thing, but if you have a look at the ALMA data, there is no sign of such a third object, so it's kind of mystery. But it has this spiral structure in the CO, so probably induced because of the binary. But after looking at many of, this is just a continuum map in ALMA. This is the Myra A. This is Myra B. We never seen any sign of mass transfer, jet coming from the companion, whatever thing that can tell you that there is a strong interaction between the two stars, apart from reshaping a little bit the envelope, producing these spiral waves. Of course, if you have a look at some symbiotic star, which is a red giant plus a white dwarf with mass transfer in action, then you get nebulae that really looks like planetary nebula, but this is not a planetary nebula. This is due to the jet that is coming from the white dwarf. There is no ionization. This is not ionized because the UV photons of the white dwarf. This is all ionized because of the shocks, because the white dwarf accompanying the Myra is releasing a very powerful jet that you can observe from centimeter wavelengths in the radio up to X-rays. So this was very well known in the past. What we have done is to compute for the first time the orbit of the system by combining thin measurements of the position of the two stars. This is always the Myra, and this control you see is the position of the jet at different epochs. This is a VLT observation. This is not ALMA. The rest of these things are ALMA data. Even in some cases, we thought we were watching mass transfer. This plus the radial velocity curve for the primary, again from SIO masers that we are running with a gap since the 80s in the last century, and some old data. We can do a fit, and we see that we get a period of 42 days that was known before with a larger error, but the separation goes from 10 to 27 AU. So at those ranges of distance, we do have interaction, a strong interaction. We can release jet. These jets could reshape the AGB envelope in the future, let's say. Another example, very recent from people here in Belgium. This is V Hydra. This is a carbon star. It's also semi-regular. And it was known that the shape of this AGB envelope was not standard. It consisted of a fat disk, which is expanding, not rotating, and some ejections in two opposite directions perpendicular to the disk, with velocities up to, without the projection, up to more than 100 kilometers per second. Well, very recently, Planck et al. Discovered that around V Hydra must be a companion with a 17-year period, and the separation is of the order of 11 AU. So again, if you are close, so close to as 10 AU, 20 AU, you probably can launch jet and reshape an AGB envelope. If your orbit is several hundred years, you probably are too far away and the interaction is too weak. Anyway, if we move into pre-planetary nebulae, those nebulae around post-AGB stars, and this is a personal classification. From my point of view, there are two classes. There are the problematic ones and the non-problematic ones. The problematic ones are these ones. I call it large momentum, because when you cartography this nebulae in molecules and you compute the linear momentum in this outflow, it exceeds by several orders of magnitude what you can power through radiation pressure on those grains. And this is the mechanism that works for an AGB envelope. Okay, where you're in the AGB, radiation pressure on the grains, push the grains away, the grains drags the molecules, and the whole envelope expands. But you have a maximum amount of momentum you can transfer this way. In this kind of sources, typically, we are off by a factor of 100 or even more. The energetic, in this case, in this type of sources, are impressive. And of course, they are all bipolar or multipolar, etc. And we all ask, I mean, everybody in the field wants to find a rotating disk in the middle, a companion, and a jet being launched, because it's the obvious explanation for this kind of shape. The image you see in the color is reflection taken with HST. The black contours is the skeleton of the CO. This is OH masers. This is forbidden atomic lines. So you see there are some shocks along the axis. So something went in this direction that reshaped the whole thing into that shape. By the way, most of the mass is contained in these walls. Okay, there is reflection in the dust, but the mass is very thin. This is the equatorial waist, the lobes, and these lobes have little mass at all. But the speed goes here and there. Okay. Another characteristic of this object is in most cases they are self-similar, meaning that if you are farther, you are also faster. You are receding from the center faster. It's a simple Hubble-Lemaitre law, which tells you that maybe there was an explosion in the middle some time ago. In this case, 1,200 years ago. The other case are the non-problematic, but nevertheless interesting, is the kind of stars that Hans van Winkel and his group has been studying since years, and they are low momentum. That means that they also get bipolar winds rich in molecules, but those you can explain with radiation pressure. And where you don't need any binary, any jet, anything special, is where you find that all these objects are binaries. You have a post-AGB or maybe post-RGB. There is a main sequence companion. There must be an accretion disk around the companion. The companion is releasing a jet, and you have a Keplerian rotation circumbinary disk around. All the elements you need to have for explaining the very powerful, we only find them in this, which in terms of momentum are pretty weak. Other properties, well, we know that these Keplerian rotating disks are long-lived structures because the grains are being reprocessed. We know that the stars, the two stars are poor in refractory elements because they have been reaccreting material from the disk, but only the material that goes not into the dust. That's the only way of explaining this refractory element depletion in the atmosphere of the two stars. And as I said, there are also bipolar outflows coming from the companion, probably driven by an accretion disk. And you can observe, you can do optical interferometry and observe the inner rim, or you can use ALMA for example, with lower resolution to cartography the outflow, which, by the way, most of the mass of the system, apart from the central star, is either in the outflow or the disk or in both components. So the most of the mass of the whole envelope is in this part of the in the disk. Again, this is M182. It's an example of what we have been doing in this. As I said, we have the CO in these walls and the equatorial waste. Then there is some forbidden emission telling you that there are shocks over there. And as I said, the velocity low can be explained as a sort of Hubble-Lemaitre expansion with kinematical age of 1200 years. In the new modeling we are doing by a PhD student with us, he has been fitting maps of 8 different molecular lines and also the single disk data of another 15, including all these species. And we got some interesting results, like this ratio is telling us that the AGB evolution of the object was interrupted. I mean, the final abundances are different what model predicts if you end up your AGB completely. These blobs are much younger, and also we have found changes in this ratio, this isotopy ratio between the shell that is 1200 years old and the one that is 600 years old. So there are changes in the isotopic composition at the very last moment. And again, the numbers are incredible. The mass of this envelope is 0.6 solar masses. And this is the linear momentum, and this is the total energy. These kind of objects are also called ILOTs, intermediate luminosity transient objects, because the energy you require to power this thing lies in between novae and supernovae, something that sort. So you can imagine what kind of thing you need to do this. The other example I want to talk about is the red rectangle. That's probably the prototype of the, let's say, non-problematic sources, the post-AGB binaries with circumbinary rotating disk. It has this funny shape, this rectangle, well, X shape, but this is not light reflected on dust. This is kind of fluorescent. It's called extended red emission. This is PAH is emitting light in the infrared. So this is not reflected light on dust. The dust is always concentrated at the equator. Thanks to the work here, we have the period of the binary, the mass of the central star, and if you cartography CO, what you get is this. In green is the moderate velocities, and this is the blue shifted and red shifted. You see a rotating disk in the middle and a low velocity outflow coming out from the disk. We also think that in the middle there is a photon-dominated region, a PDR, that is destroying molecules and forming molecules, giving rise of totally different chemistry. What we have done very recently is a new ALMA observation reaching this resolution, which at the distance of the red rectangle is 14 AU. This is for the continuum. For the lines that are noisier, we had to remain at 40 AU resolution. And that's just what we got. We got that at millimeter wavelengths, most of the emission comes from a central component, very compact, and a very flat, thin disk. Okay, the disk is much bigger, but most of the emission comes from very, very thin line. Okay, if we combine, that's some of the tricks you can do with interferometry. If we reject all the short baselines, we filter out the extended emission, we keep only the compact thin, and we can isolate what the flux of this compact component is. And what is remain is the disk. So we call the compact central component and the disk dash component, okay? If you compare these results with those at other wavelengths, we realize that this component has this spectral index, the compact component has this spectral index. This is almost flat in emissivity. Nu square means that you emit as efficient, equally efficiently at all wavelengths. This is the typical spectral slope of a black body, or something that is not black body, but its emission spectrum is flat. Okay? The only way to get flat emission, well, this is not a black body, but if you assume how much dust you may have at this frequency, to have this frequency opaque, it doesn't make any sense. You end up with solar masses. Okay? So the only way out is that the emissivity is flat. And the only way to have dust emitting efficiently at all wavelengths is that the grain is bigger than the shortest wavelength you are observing. We did our observations here, but we also have hints that the goes like that up to 30 millimeter, meaning that the grains had to be at least as large as 1 centimeter or so. Otherwise, you cannot explain this trend. By the way, the other component has a spectral index of 0.8, which is very close what is predicted for ionized wind with a constant mass loss. Remember that the companion is releasing ionized wind. So this, we believe, is the ionized wind from the companion, and this is the emission from a disk where the presence of with the presence of big grains. There is no way out. Well, this is the model we built. This is the results. If you want to compare, well, pretty much the same within the fitting errors. The mass of this disk is around 25 Earth masses, which is not huge, but still, no. As I said, the disk is pretty small, and this, by the way, has already been published. If you have a look at the molecular lines, again, you see the wind at some velocities, and when you get to the center, you see emission on one side, and then coming to the other side at the signature of the rotating disk. Okay? CO is much bigger, it's wider, the disk is wider, it's larger, simply meaning that the grains that are efficiently emitting at this wavelength are more compact, are more concentrated to the equatorial plane. We haven't seen any sign of gas depletion, and that's not a surprise because these disks are not cool, are warm. They are at least 300 Kelvin, and at those temperatures you don't expect to have gas depletion on the grain surface. This is a velocity position diagram, and you clearly see the signature of a Klepperian rotating disk. This is the famous hyperbolic shape, but if you want to reproduce the limiting space of the CO, and you want to not to get in trouble with the total mass that has been derived for the Celtran system from the orbital from the optical, then you need to assume that there is also expansion in the disk. So it's not a Keplerian disk, it's sub-Keplerian. You have rotation following a Keplerian law, but you also have expansion at all distances. We don't see anything in the middle simply because CO has the same temperature as the continuum, more or less. We have to subtract the continuum because otherwise you don't see what is continuum, what is line. And if you subtract 300 minus 300, you get nothing. But it doesn't mean really that there is no CO in the middle. It simply is the fact that the CO is opaque and you are subtracting the continuum. There's no way out. Not only CO, we have seen, well, this is 13 CO. Again, this is a zoom in into the central regions. Well, again, we also have seen H13CN coming just, this is kind of a straight line, but this is what you expect just for the inner rim. If you think about it, you have an inner rim which is rotating in a Keplerian rotation. The projected velocity is a straight line. And same happens with HCM bibrationally excited. This is water bibrationally excited, and this is SiO. This is very faint, but this is SiO bibrationally excited. These are the excitation that those molecules require. This doesn't mean that there is hot gas there. They are pumped by infrared radiation, and the source of infrared radiation must be the dust itself. The infrared photons pump the molecules up, so we don't need to have gas at that high temperature to explain the existence of vibrationally excited water. As you see, we have oxygen-rich molecules, carbon-rich molecules. This mix of chemistry, it's not okay for an AGB envelope, but this is not an AGB envelope anymore. We are talking about molecules that are being destroyed by the central sources and being reformed in conditions different from an AGB, and then this area, this region pretty much looks like a photon-dominated region, a PDR. By the way, we detected with Herschel C1 and C2 lines, and there is also PAHs, as I said before. So it pretty much fits what you expect for a PDR environment. What's next? ALMA observation with 4 AU resolution has been already scheduled. Let's see if we can get something out of it. And targeting also C1 to study the PDR. And at longer wavelength, we have just been approved for meerkat observations. The resolution is very poor, but of course this is to get ourselves ready for when SKA, the square kilometer array, is ready, because the only way to really prove and map the existence of very big grains in these systems is by using the longest wavelengths you can get, but of course you must be able to map it and be sensitive. And for that you really need to have very large arrays. Okay? With this resolution we can only do the red rectangle with the pathfinder of SKA in South Africa. This is the part that Ivan should have speak about. I'll try to go fast because I've been granted with the slides just yesterday. When we study not on one single object, but many of them, which in the case of molecular lines, we end up with 11 or so, we found that if you compare how much gas mass is in the disk and how much mass is in the outflow coming out of the disk, we have some sources in which most of the mass is in the rotating disk, and some sources where most of the mass is in the outflowing wind. And there is no in-between source. So we propose to separate these post-AGB, RGB objects with binaries and circumbinary disk into 2 categories from the molecular point of view, the ones that are disk-dominated and the ones that are outflow-dominated. Of course, this is small statistics, but getting good cartography to separate which CO emission comes from which component, you need to have good cartography, and that means probably not NOIMA in the French Alps. You probably need ALMA in all the cases. And then it takes some effort to have all this cartography. This is an example, the red rectangle of a disk-dominated source, meaning that most of the CO is contained in the disk, whereas in 89 Hercules, we also have a rotating disk, but most of the mass is in this huge bipolar outflow. Again, it's an outflow at low velocity. We can explain by just pushing the grains by radiation pressure. I'm not saying this is the mechanism, and I'm just saying that this source's energy is enough. Whereas in the other cases we were discussing before, this is simply ruled out. Another property of these objects, if you compare the relationship, this is the nebular masses of all objects we have studied in CO, but the ones in the middle, we don't know whether they are disk-dominated or outflow-dominated because we only have single disk data. Okay, we know the total mass, but not which mass goes into what component. They are poor in molecules. When you take the infrared emission and you compare with molecules, they are way down what is normal for AGB stars. So if you compare these guys with AGB stars, even with the other protoplanetary nebulae, the one that have large momentum, these are molecular poor. I mean, most of the mass is still in molecules, but the ratio between the dust component and the molecular component is lower, except for one species, 13CO. And this is why they are very rich, systematically rich in 13C. For whatever reason, we don't know yet. Okay, so this is just a plot showing different ratios, but they are always below what is normal for the other kind of preplanetaries, etc. This is more or less about the same. These are new detections, even in OH masers, water masers, and SIO masers in these guys. This is very important because to have, for example, SIO masers, you need to have densities of the order of 10 to the 9th. Otherwise, you don't explain the existence of SIO masers. And in these objects with circumbinary disk, it means that we need to have a region where at least the gas density is 10 to the 9th, which is kind of constraining. We are trying to find correlations between this outflow dominated with other parameters, and I think the most promising, let me skip, is this one, is when you compare the luminosity at long wavelengths divided by the mass of the envelope. Of course, the more massive the envelope or the disk, the more grains you have. So if you take this ratio, that's, we think, is a proxy of how much big grains are in these structures. The disk dominated show a much larger radio than the outflow dominated. And our explanation will be that if you are really powering these winds, the molecular winds, the ones you can power by radiation pressure, that only works if your grains are small. If you try to push a 1 millimeter size grain by radiation pressure, it's not going to work. 1 micron size, it works. So the apparently correlation will be explained. Maybe this dominated, what happens to them is they cannot release a very powerful wind because they are poor in small grains, where these others are still rich in small grains and not so prominent in big grains. And I think that's solved. Thank you for your attention.
Thank you, Javier, for an interesting talk. We have some time for discussion. Don't be shy.
Hi, thank you for your very interesting talk. I was wondering, because you mentioned that your 12CO and your 13CO, either or both, are optically thick.
Yeah.
So how do you determine the 12C over 13C ratio in that case?
In that case, I think it's difficult. So we have been determining the 12C over 13C ratio from single dish, but it turned out in this case of the red rectangle with the good cartography that 13CO is almost optically thick also in the disk. Okay. You can still derive isotopic ratios in the regions where the opacity is not so big, but the fact that 13CO is almost thick is telling you that the ratio is pretty low. It's extremely low. It cannot be 20. It makes no sense. It has to be of the order of 10. And this has been found in many objects of this class.
Okay, so you mainly determine the actual ratio for the disks where they're not optically thick?
Yeah.
And it's still relatively small. Okay.
Yeah.
Thank you.
Hi, Javier. On page 8 of your slides, you have shown how you have determined the orbital parameters of Era-Curie system.
Yeah.
I have to admit that I missed somehow these publications, but how have you then, if I understood you correctly, you also have used SIO-Maser data to do so? Can you potentially explain how you then are estimating the parameters given the SIO-Maser data?
Okay, we have on one side, we have the radial velocity curve for the primary. We have a couple of points here I didn't mention. These blue dots is the mean velocity of the radio recombination line coming from the companion. So somehow we also have a couple of points telling us about the companion velocity. But this is SIO-Masers. Yeah, this is SIO-Masers. This is not, it's a little bit tricky. What we have done, and we believe is the thing that works best, is you take your spectrum. We are taking a spectrum every month since many, many years. And you compute the midpoint of the two extreme velocities you measure, because this is amplified. And then taking the mean velocity doesn't tell you anything, because you can have one strong spot here, there. So it's the middle point between the two extreme velocities. And this is this point. I have assigned an error, because you always have an error, but I don't know. I mean, this, how big this error could be is difficult, but you still see. This is optical data, okay, corrected for, I mean, it's an old paper by Gromadski and Mikolajewska. Those are optical data that have been corrected, but because some shift is known that you have to do it that way. But from here is only SIO data from the old days, the beginning, the discovery of the SIO-Maser or monitoring, then there was a gap here, and then the new monitoring.
How can you then determine the inclination? Is that very much, I see it's quite
because we
constrained
always
there.
have I mean, we have the relative position between the two objects. This is always, I mean, the center is always the radio continuum, the strong radio continuum source in the ALMA maps, or in the case of the BLT, the one you see in the continuum. In the BLT, which is this spot, in the continuum you only see the bright Mira, but in H alpha you see the Mira as bright as the companion. Okay, they know which one is. So, and this is the spot of the companion at the time of the BLT observations. These contours were the radio observation with ALMA at one epoch, 17.9, so it's 2017.9. And we suspect there was Mira, of course, and there was the companion, which makes sense. These green contours, we fail in separating the both components because they were too close, but this is the middle velocity of the radio jet seen in radio recombination lines, so the companion must be in the middle. This is continuum observation, and these are also continuum observations where, again, I'm assuming that the companion is at the base of the jet. Don't ask me why this is a one-side jet, but it's a one-side jet. I mean, there is no jet coming this way, so we know that the companion must be at the apex. Previous tentative detection of the companion was up here in the 90s.
But is
it was totally, sorry, it was totally wrong. But if you estimate where the companion was in the 90s, it's around here, and it's just the jet. It was a big spot like that. Is the jet. It was the jet coming out.
So the red contours are in
continuum.
Or continuum, sorry.
Yeah.
Aren't these, if you say it's potentially only a one-sided jet, so
yeah.
It's not the remnant of a spiral-like structure then?
Sorry?
The remnant of a spiral-like
structure?
No.
The spiral structure you see in CO, there is a spiral structure coming out like that, exactly as you expect if you have this kind of rotation. No, this is jet coming from the companion only.
We still have time for questions.
Thank you. at the end of the talk in Ivan's part about the difference between the disk-dominated and outflow-dominated related to the grain size, do you think this is just a different evolutionary phase where the large grains are just more evolved, or is there another physical process that's stopping the outflow-dominated sources from actually growing large grains?
We have been discussing this issue over the last 3 days. We don't know what to tell. Still, this 1 millimeter luminosity divided by mass is a kind of the only thing we have found that separates this dominated between outflow dominated. We are still not sure whether this is significant or not. It's few numbers. What we need is more fluxes in the millimeter regime and do the big statistics. Now, if this is an evolutionary or not, I will say that if this is an evolution, you should see some objects transiting both stages. Or maybe the evolution is too fast, I don't know. But with these 7 sources, we run into the problem of statistics. We all agree that we need more data. And that means more millimeter data. We already agreed on that. And about getting more cartography on these things, well, we'll talk about it. But we also need cartography for more objects, because otherwise separating the 2 components, you can do it from the spectrum, okay. Okay, the disk is the narrow thing, but you don't want to do it that way.
Thank you.
You are not being recorded.
Yeah.
So we tried many parameters in a parameter study to eventually separate the 2, but apart from the outflow and non-outflow, there is not a very clear connection to any other property of the disks. So but it's clear that the growing to very large grains is very fast.
Also, the existence of very, very large grain is based on this plot, centimeter size, and separating the compact component and the extended component in all VLA data. It was complex. It's a paper by Jura et al. In the 90s. They speak about a compact source with that flux, and then the total flux, which includes some extended thing. So I subtract, but the resolution was very poor. So I assuming that the extended means the disk, and the compact means the outflow, because if this is a ionized wind, you can compute how big is it at the different frequencies. It's very easy, and it will be still compact in the all VLA data. But you would like to have a map where you see the disk and the compact at the middle and separate that. But we also tried to get new VLA data for the red rectangle, but we were rejected. Maybe the ALMA observations are online, but you never know if you are not A. Maybe they don't do it. So far, we have been able to get some time for the red rectangle, because it is always at the right extension where there is not a lot of pressure. If we get data, we probably can convince the VLI guys to do it, the long wavelength part. But you know how it goes. Apparently the referees thought that there was no relationship between the existence of big grains and the formation of planets. Don't ask me why. I'm not an expert on planet formation. But they claimed that it wasn't sure. So if you detect centimeter-sized grains, so what? Well,
Okay, we still have time for questions.
Hi, and thanks for the nice talk. It was I find the statistic you had on your very first slide very interesting, that 85% non-symmetric compared to, say, roughly 50% is what our best estimates of low mass star binarity are.
Yep.
I'm just wondering, could you speculate on what you think maybe the root cause of that discrepancy is?
Well, I can tell you what people think in the community. What people think is that if you have a companion, at some point you are going to suffer a drastic mass loss, exactly when the interaction is strong enough. And instead of losing your mass steadily along the AGB evolution is going to be stopped suddenly, because you are going to lose what is rest in your envelope, in your sterile envelope, in one shot. Now, of course, if that happens to you, then when you become planetary nebulae, there is still a lot of mass around. You can ionize, and the planetary nebula will bright and shine. I mean, you could detect it. Whereas, if you are alone, you are a single star, maybe what happens is that you lose mass at a moderate rates, increasingly with time, but not any sudden whatever. And then it may simply happen that the time it takes you to evolve from the end of the AGB to the point you are able to ionize your matter around is so long, but when you shine again in the UV, there is no matter left to illuminate. So those nebulae will be there, but probably too faint, without details, very smooth, and then try to recover that against the background. It's simply more difficult.
Okay.
That's the idea, but I'm not saying this is the solution. This is what people in the community is speculating. So if you are by yourself, then you will die peacefully, and nobody will notice. If you have the help of a companion, then you can die, with fireworks, and everybody pay attention to you. That's the summary of the talk.
Thanks very much.
Still a bit of time.
So talking about these companions, so you say that 50% of these stars have companions, and these are stellar companions, which we can see, right?
Yeah. No,
So
in the planetary must be stellar. Yeah.
So we can see also like very massive stars, or massive stars in general, that have like on very wide orbits, like brown dwarfs or solar-like companions. So in principle, if they go core collapse and have no kick, this system should remain bound. So could they compensate for this discrepancy?
Maybe too, yeah. As I said, the 50% binarity at the center of planetary nebulae, it's only a limit. I mean, if you could detect, I don't know, super Jupiters, maybe you detect a super Jupiter, they may also help you to reshape your nebula at some point. I mean, the consensus is that either we get energy from the gravitational orbit, or there's no way we can power those winds for the problematic ones. For the one Hans has been studying since years, we don't need that energy, but we do find the binaries, and we do find the rotating disk. There is only one source among the very energetic where there's a rotating disk that has been found. It's called QX Puppis, or the Calabash Nebula. And it was found because you have a look at CO, there's CO everywhere. And we had a look at sodium chloride. And sodium chloride is found at the very inner part of the envelope and is rotating. But we don't know whether it's a binary there. We know that there is a little rotating disk in the middle, and we know that this guy has a wind which is 300 kilometers per second in molecular lines. That requires some jet at some point, otherwise no.
All right. So Javier, our main astroseismologist is not in the room, but I have some little connection, so I have to step in. In the beginning of your talk, you mentioned that post-AGB stars are high-amplitude pulsators.
No, no post-AGB, the AGBs.
Or AGB stars. Hence my question actually too. What is the role of pulsations in powering and possibly shaping the outflows that you observe? And second question would be if there are any unknowns in the interior structure of these stars that astroseismology could help to shed some light on?
Okay. The pulsation. The pulsation is fundamental to explain the mass loss in all these objects because, as I said, the expansion comes from the radiation pressure on grains, but you have to have a layer which is cool enough and dense enough to the grains to condense and grow. Otherwise, it doesn't work. And the only way to explain that is pulsation. Without pulsation, no mass loss. Now, if the pulsation is not, obviously is not going to be spherically symmetric because you may have also hot spots, cool spots in the atmosphere. That favors the formation of grains here and there. If this is chaotic, I wouldn't expect reshaping on the large scale. If it's systematic, if you tell me that there are some stars that are cooler on the poles and hotter in the equator or the other way around, maybe they manage to have non-spherical envelopes and then the interaction reshapes the whole thing or whatever. But in the case of supergiant, people think that because the mass loss we observe in supergiants at very small scale is very puffy. That's probably because we form dust preferentially in this spot this time, the other spot, because of the role of the different temperatures in the photosphere and this requirement of having a dense layer of rich and refractory elements, but below some temperature. In the case of carbon stars, probably below 2000 temperatures, 2000 Kelvin. In the case of oxygen-rich stars, you have to be even cooler. 1000 something, which also poses some problem. People think that first you nucleate things made of aluminum and magnesium and then the silicon sticks on it. So that's, I mean, there's a lot of work going on this and it's not totally clear whether you can explain the grain formation at all, at least in oxygen-rich stars. But true, I mean, without pulsation, you don't do anything, that's for sure. In the case of supergiant, they don't pulsate strong enough, but they have this, convection cells, big convection cells, and that may help because you see that the mass loss is randomly organized.
Okay, thank you. We are at the hour, so we are going to stop here. Let's thank our speaker again.
Thank you.
Thanks for coming and see you next week.